Hello, everybody. It's very nice to be here, and obviously thank you to all of the sponsors, everyone who made it possible for this to happen. Well, special thanks to King, which is sponsoring, which is my company. But special thanks to them because they pushed me to actually do the call for proposal and apply to be a speaker, and now I'm here. So that's really nice. So my name is Zuzanna. I've been a Java developer for 3 years now. Let me start a bit earlier. So I studied mathematics at university, but I was really interested in computer science, and I was asking around what can I take from computer science department, what subjects, and they were like, oh, there's just one. And I took Lambda Calculus, and I don't know if you know it. Lambda Calculus is the very, very theoretical base of functional programming. It has nothing to do with computers, to be honest. And it was very, very theoretical and hard, and I managed to pass the exam barely. And I was like, okay, let's see, what is this? So then I became a Java developer, and I've been working for various companies building object-oriented software. And right now I work at King, building infrastructure to operate games like Candy Crush Saga and other games that we have. So I've been doing this for 3 years now, building the object-oriented software with all of its benefits and disadvantages. And I started realizing what this course was about because I started seeing the problems that the Lambda Calculus with functional programming would take away from me. And I got interested in functional programming, rediscovering this course that I took. So that's why my talk today is about principles of functional programming. It's a topic that I'm very interested in. I'm learning about it every day. Sadly, I don't get to actually work in it, but we're trying. And yes, I do it through learning Haskell, which is the most sort of hardcore functional language right now. And it's really fun. So what is functional programming anyway? It's a programming paradigm. Just like object-oriented programming is a paradigm as well. It means that they are a way of looking at a problem and solving it. And they are fundamentally different. But interestingly, the functional programming was invented first in the 50s, in the very beginnings of software development. But then it sort of stayed hidden from the public because it was used mainly at universities by academia. And over the years, object-oriented programming became the norm to use in commercial software. So let me start with a quick overview of the object-oriented programming principles. Here they are. I'm not going to go into much detail about them because the thing that I want to really focus on is the general idea. So in programming, there's always some data, and this is the stuff that program knows about. And there's always some behaviors. So this is the things that program wants to do with the data or to the data or something like that. So object-oriented programming says that those two things, the data and the behaviors, belong together, that they should be put together in what is called an object. And that way you have the data really coupled with the actions that you can do to it, which we call methods and things like that. So the idea is that we put together the data and behaviors, and then they talk to each other, to other data with its own behaviors. And now, functional programming has a totally different view on that. They think that data and behaviors are fundamentally different things. They should be separated. And you'll have data on one side, and then you have behaviors that don't really care what the data is. So that means that you have functions that usually take the data in and then transform it, do whatever they want, and then give away the new data, the transformed data. Interestingly, both paradigms claim that this is to make the code easier to read and easier to reason about, even though they're completely different things. Okay, so let me talk about functional programming principles. What makes this paradigm functional is use of pure functions. We're going to talk about functions a lot. That's why it's called functional. And pure functions are defined by some properties that I will talk about in just a second. Then another principle of functional programming is immutability. They put a lot of effort to make everything immutable, unless you have a very good reason to not to. And immutable means that once you create some data and you assign it to some name to talk to it, then you cannot change it anymore, which is quite strong, quite drastic to say. And then the last principle of functional programming is treating functions as first-class citizens. That means that functions are the same as variable constants in other languages. So you can create a function that takes a function as a parameter, and you can create a function that returns a function as their result. And here I put some examples of languages to talk about what it means. So for example, Java is a very object-oriented language. That means that its infrastructure is well prepared to do object-oriented programming. It's not really well prepared to do functional programming, but there are some recent developments in features that are functional style programming. And that means that if you want to enforce yourself to keep things immutable and write pure functions, then you can get some benefits of it even within Java. Then there's Python, that's also an object-oriented language, but there are also libraries that help you do functional programming in it. Then there's Scala, that's somewhere in between. So Scala has all of the properties of Java as well, but it has some things that make it easier to do functional programming in it. There's even JavaScript here. That's very multi-paradigm. You can do either object-oriented there or functional programming. There's a lot of frameworks and libraries that help you do that. And then on the far right, there is Haskell, which is very functional-oriented. So it was built around the functional programming idea. It's almost the same as the Lambda Calculus, the theory behind. And it would be very hard to write object-oriented things in Haskell, but you could probably try. OK, so what are pure functions? And we need to understand that because we'll be talking about that a lot. Pure functions are deterministic, and they have no side effects. What does it mean that a pure function is deterministic? That means that whenever you give it some input, then it gives you some output. And if you give it the same input again, that you will always get the same output. So, for example, say that you write a function that returns you when is the next Tuesday. So if you run it today, it will be the next Tuesday. But if you run it in a week, then it will be a different Tuesday, because the next Tuesday is already different. So this is not deterministic, because depending when you run it or in what circumstances, it will give you a different output. But if you think of a function that returns all of the Tuesdays in a given year, well, that's great. That's deterministic, because these things don't change. You just ask for the year, and you get all the Tuesdays. The other property is having no side effects. Side effects here mean changing the global state of an application or depending on global state of the application. That is basically, that means that the function doesn't affect anything outside of its own scope, and it also doesn't depend on things. So the classic example here is printing to the log, printing to the console. So what are the side effects there? Well, you run your function, and obviously the effect that you can see very visually is that you printed something. But that depends on the console, that you have to have the console, you have to be able to print it. There's so many things that can go wrong that your function is no longer independent in a way. So that's what no side effect means. Here are some examples of pure functions. The first one is very, very simple. It takes two integers and returns you the maximum of them, like the bigger one of both of them. There is nothing here that depends on the outer state of the function, on some global variables or something. Whenever you give it the same numbers, like 2 and 3, it doesn't matter if it's raining or where you are, it will always be the 3 that's larger than 2. That's great. It's a great function. And then the second one is giving you the timestamp of, for example, in 3 hours. So as long as you provided the current timestamp, you provided how many hours, you do the calculation, you will always receive the same output with the same input. So here are some more examples, and these are the not pure functions. Specifically, the last one, I don't know if everyone can see it, but specifically the last one is a different implementation of the second one that is not pure. So here we don't depend on input to know what is the current timestamp. Instead, we take it from the current timestamp itself. And this is depending on the global state, because now if you run this function now, you get the result like in 3 hours or whatever. But if you run it in 1 minute, the output will change. And none of the input to the function changed. So this is not pure anymore. And the middle example is the classic example of depending on changing the global state. So here, say we have some button, and you can click it, and it counts the clicks. Now you store somewhere this counter, and this function gets invoked when you click the button. And here it just increments the counter. Well, this is not pure at all, because whenever you run it, you change the different state, you depend on states, and this is not very pure. But why would we care about pure functions anyway? What's good about them? Well, if you have a function that's deterministic and have no side effects, it's very independent, and it gives you a very, very comfortable way of using things. So, for example, you can run it. You don't ever have to worry that if the global state changed or something, the function will be affected. You can run it whenever. And that also extends to the idea that you can run it in parallel to anything else, because there's nothing that can happen in parallel that would break your function, because your function is independent. So this is really great for concurrent computations and for safe computations. It's also very, very easy to test, because you don't have to mock any state. You only need to test that with given input, the output is what you expect. And this is very easy to do. And here's another thing that's pretty cool. It happens when you have a pure function, and you also agree to have immutable data. So what good can come from both of them? So here, imagine you have a function that, as an argument, takes a dog, an object of type dog, and it does something to it, returns you a number. It could be number of paws that it has, number whatever. So now comes the immutability part. Say that we agree that the dog, this exact dog, in this way, in this example, Pam, like once it's Pam, it will never change. If you want to change it, you will create a new dog with the changed properties, so to say. So now you run the function, you run it on Pam, and you get some result, for example, 72. So now you know that the function is deterministic. It will always give you the same result, and you know that Pam will never change. So what that means is whenever you invoke function of Pam, you will always get 72. And that's very powerful, because now you can treat it as a value. You can say it's almost as if you had a variable, well, as a constant in this case, that's called function of Pam. You just substitute it for 72, and you'd never have to realize the computation again. So this is very, very powerful concept that's used in memoization or caching and things like that. So it's quite cool. OK, so we have all these things. We have super cool pure functions, don't depend on anything. We have immutability. We can't change anything. How can we do anything with that? How could you make something happen? Apart from making your processor really hot from all the computations, of course. OK, so the functional programming is not about making everything pure and immutable, because obviously you will not achieve anything. It's about making all that can be made this way, and having clear visibility of what are the parts of your program that depend on other things. What are the parts of your program that change other things? And that means that you can make, for example, 90% of your program pure, absolutely testable, easy to reason about, independent and everything. And then have all of the state changing, all of the side effects in just the 10% that you encapsulate either like at the end, for example. And then you know that this part you have to test differently. And this part is the dangerous part. But you can't have it mixed altogether. like you sort of do in the object-oriented programming, because then it would break the functional programming things. In practice, what it means is that your functions, if they produce side effects, they have different type. A special type that may let you know that this is a function that's not very safe, that's not pure. And this type, whenever you use that function, well, you have to pass this type on. So it's sort of like a stain. It like keeps staining parts of your program that depend on it. And so you have a clear visibility that if the function doesn't have it in its type, well, then it's pure, it's clean, and you can test it freely. And if it does, then you have to be careful about it. Cool. Now I would like to talk about two concepts in functional programming that I found very interesting. They have some interesting benefits and some surprising properties, probably. So first, immutability. What does it mean to be immutable? Like I mentioned, is that once you create the data, you don't want to change it ever. So that seems very strict, but we actually use it every day anyway, and we depend on it, maybe without even thinking about it. A good example of that is numbers. So whenever you talk about number 2, you really believe that it's going to be 2 forever. You don't want it to be able to change because that would break everything. So, for example, numbers are immutable. Whenever you create a number, in this case 42, in all of the 3 instances, it's the same 42, and you assume it will never change. You assume that no one has any right to change it. So what is the benefit? Well, you can only create it once, and then point to the same data all the time. You save on space, and then you get this safety that this is the 42, and it will never change. And I can use it always with all of the benefits of the security. So yes, this example is just showing that however you create the number 42, it will point to the same data in the memory. And here's another example of immutability. What happens when it's sort of forced? So in Haskell, this is some Haskell REPL code. In Haskell, everything is immutable, and it's forced by the programming language. So what happens in Haskell is that you can create an array called A of numbers from 1 to 3. And there's a function called reverse that reverses the order of numbers. So we call that function, we say reverse A. What we get in back is 3, 2, 1. But then if we want to see what's A again, it's still 1 to 3. So the original array never changed. What happened is that the function returned a transformed array and didn't touch the original one. So whoever else wants to still use the original one, they can do it safely because they know that there is no way that someone else could change it in the meantime. So what else? Let's think about something even more from this. So that means that if you have an object that has a lot of properties, and you only want to change one of them, well, you need to create a new object, which sometimes can be a disadvantage, obviously. But here, let's see what are advantages of it. So the example is trying to show that if you have a black circle and its reference is 1 in the memory, then if you create a new one that's gray, well, if you want to change the first one to be gray, you need to create a new one that's gray. So now you have 2 objects that are very similar. They're just changed by 1 property, but they are new objects. So how could we use that? Now a good example here is think of a time when you need to know if something changed or not, if the state has changed. So say you have a web application that the UI of the web application is defined by some global state, and that tells you how to render your application, how to draw all of the application. And then you don't want to do the drawing unless you have to, so unless something changed. So you would like to have a quick way of knowing if the state changed and you need to redraw the page, or if the state hasn't changed, then you don't have to do anything. With immutability, if the state changed, if anything, even one thing changed, it will be a new object now, new piece of data. So now you'll see that the only thing you need to do is compare the state you have with the new one, and if it's not exactly the same piece of data, well, then you have to redraw it. But that can save you a lot of time of going field by field and looking for the difference. In Java, what that means is that if you have, for example, a string that's immutable in Java, and then you do something to the string, and you return a different string, if the function that you did only passed you back the string, so it didn't change anything, the only thing that you need to do is do a pointer reference comparison, which is the double equals in Java, and you don't have to implement the equals function, because that way you already know if something changed or not. And if something changed, then you can do something about it, and if it hasn't, you don't do anything. The last thing about immutability is a use case when, well, writing any program, there's some things that you don't want someone else to change. There are some things that you want to stay the same, or you want just you to be able to change it and not someone else. So basically having some things that you don't want others to be able to touch, or you want others to be able to see it but not to change it. What happens in object-oriented programming is you have ways of restricting the scope of access to objects, and you use private or final keywords to do that, and then you provide methods to interface with those data for others. What you do in functional programming, you just exploit the immutability. If everything is immutable, then no one can change anything. And then you don't have to worry about private. Like, there is no private keyword because it doesn't make sense anymore. Everything is private, so to say. But if you are the owner of your data, then you have the power to decide what you show to others. So no one else can change your data, but if you choose to change it, then you create a new one, and you announce that this is the new sort of source of truth for others about this data. That lets you to be owner of your data, but keeping the immutability, and not having to worry about the actual scope of access of others. The other thing I want to talk about here is null. And I found it very surprising when I was learning functional programming, and especially Haskell. There is no null in Haskell. There is no idea of null. So, but there is null in most of the other languages. I don't know if in most, but in the ones that I used, there was always null. When do we use null? Why do we use null? We use it when there's nothing to return, when we don't know what to do, when we want to say that there's something, but maybe not, maybe there was an error. Like, the use case is a bit vague, and you always use the same null for it for many, many uses. So that could be confusing, I think. Here's an example in Java about it. Let's see if it shows what I want to say. So let's say we have a map with my name and some number in it. Well, if we use the method getByKey from the map, we use my key, well, we get 4. That's great, we get the value. What happens if we call getByKey with a key that's not existing in the map? Well, we'll get null. That's great. So what does it mean? That means that, or at least we can think that means that there is no key Anna in the map. And we can probably take it as the information coming from the map that there is no such key in it. But now let's break it a little. What happens if you put in the map Anna and null as its value, which you can do in Java because every object can be null as well. So here integer can be null. Now we call again getByKey Anna, and we get null again. But now we know that underneath there was a different reason for that null. But we'll never know it from outside because the value is exactly the same. So it's like, it wouldn't be nice to know if the key was there or not, if the null means that there's no key or there's no value. What is the problem here? What I'm trying to show is that the method getByKey claims to be returning an integer. And then that means that it can return null as well. And now we know that there are use cases when the null is perfectly justified here, and there are use cases where null can mean two things. The return type is still integer. But now think about it. the plus operator on integers, if you add two integers, it will also claim to be an integer. Like, it has the same return type. There is absolutely no difference from the outside. But how many use cases are there that you take two integers, you add them, and you get something else, and you won't get integer? We can assume that in most of the cases, almost always, you will get an integer. So they are different, right? Get by key has cases when it will return null, and the plus doesn't. But from outside, the type signature is absolutely the same. So this is something that I think is quite dodgy, like here. Like, you would like to trust your type system, but there are ways that it can mislead you. So now I want to show you how this is handled in Haskell, and then also you'll probably see how this was sort of fixed in the latest Java features that are functional style. So let's see some Haskell. In Haskell, there's a special type called maybe for dealing exactly with this situation. So here the first line is the type construction of the type maybe. And let me show you how you construct a type in Haskell. It's actually very straightforward. So the keyword is data for constructing a new type in Haskell. Then you put the type's name, in this case maybe, and then any parameters that the type can have. So here we have data maybe A. A here, since it's not specified, it means that it could be any other type that you can think of. So it could be a string. You can create a maybe string, and it would be a type. Or it could be maybe integer, even maybe Boolean if you want to. So then we have to put the equal sign and give one or more or something constructors of the type. So in this case, we have two constructors of the type, nothing and just A, divided with the pipe symbol. That means that this type can only ever be instantiated with one of those constructors, and only one, not both, not neither, only one of them. So the first one is nothing. As you can see, nothing doesn't have any parameter. There's nothing there and nothing. So how it works is that if you have a maybe A thing, you can just say that it's equal to nothing and will be nothing. This is absolutely valid instance of type maybe string, for example. Then the second constructor is just A, which takes a parameter of the type that the maybe is the type of. So then if you have a maybe string, you can instantiate it as just hello, for example. And that means that it's an object of type maybe string with the value just hello. So let's use it in this example. Let's say that we have a dictionary, which is a bit like the map that we used in Java. Let's say we have a dictionary with one entry, my name as a key, and 10 as a value. We use the function called lookup, which is a bit like get by key. Look up Zuzanna in the dictionary. It also reads like a very nice sentence. So what we get back is just 10. What does it mean? That means that lookup returns a value of type maybe, well, in this case, maybe integer. And if lookup Zuzanna in dictionary gives you just 10, that means that in the dictionary there's a key called Zuzanna with value 10 in it. And then if we do the same for a key that's not in the dictionary, say lookup Anna in dictionary, then we will get nothing back. That means there is nothing, there's no value that I can give you back. If we try to break this example and put in Anna with something like null, in this case maybe 0, maybe something, it's not exactly the same case in Java. But whenever there's a value, you would always get just value instead of just the null, nothing, or however you could call it. So this is quite nice because you have an absolutely straight way to know if the value was there or if the key was there or wasn't. And the function from the very beginning also shouts at you saying, I return maybe string. That means that there are very legitimate cases where the string will not be there. And I need a way to communicate to you that it wasn't there. And this is the nothing. So me see. There was one more slide here, that sometimes people are interested, what can you do with just 10? How can you actually get the 10 out? And there are some functions that you can write that are quite easy to write in Haskell, that you can write a function that takes the type maybe A and extract the A from it. To do that, you need to think about what you want to extract when nothing is there, because using maybe A gives you the power to know when there was no value. But if you want to write a function that always gives you a value, then you have to think of a default value for the nothing. So this is just an example. If you have some questions about the syntax or something, catch me later, and I'm happy to explain it to you. And that was the last slide of my presentation. And I hope that I sparked some curiosity in you about functional programming. And if there are any questions, I'm very happy to try to answer them. And yeah, I think that is it.
How works the way that you test? There is many stages between the way the programming function. Is there any changes the way that you test your code? How works?
Yeah, I think that the main change here is that for functional programming, all of the parts that are pure, you can test them very directly, because you can pass them the input and expect some output. You can pass them actual values. You don't have to mock a lot of objects like you usually do in object-oriented programming. Like, in the object-oriented programming, if you wrote some utils classes maybe, where functions are practically pure, they are usually very easy to test, because you just write a test where you give it some numbers, some edge cases, and you expect some output. This is pretty much the case for most of functional programming programs. And then you have the side effects part, where you need to either write some end-to-end tests, some integration tests, where you do mock the global state of the function and see that it changes well.
Thank you, Zuzanna. It's definitely very interesting to know, but it seems that functional programming is very fault intolerant in the sense that it's all immutable. So what happens if you do make an error, and how do you deal with that? It seems that you need to define everything ahead before you write the whole program.
Do you mean that if you make an error by actually mutating something, that you want it to be immutable? Well, if you assume in your program that things are immutable and then you break that, then your program will probably break with some unexpected errors or exceptions, depending on your language. And here the catch is probably that if you use a language that enforces immutability, it's easier to trust that what you assumed is true. Whereas if you use, for example, Scala that doesn't enforce it, but it lets you use it, then you have to be a bit careful about how you do it. Even in Haskell, there are some exceptions, and people try to avoid them at all costs because they are outside of the type system, and it's quite hard to know when they will come. It happens sometimes, and then you have to debug your code normally.
Time for one more question? No more questions? Okay. Thank you very much.
Thank you.